This week, we're going to start talking about a new topic. This week, we're going to start talking about the Laplace transform. But before I do that, let me revise just a little bit from Math 2. If I want to do an integral from a to infinity of f of t dt, what this really means is the limit as some number, let's say a capital R tends to infinity, of the integral from a to capital R f of t dt. So, for example, assuming that c is a constant which is not 0, if I wanted to calculate the integral from 0 to infinity of e to the power ct dt, then what this really means is the limit as r tends to infinity, integral from 0 to r, e to the power ct dt. And we can finish this calculation. That's the limit as r tends to infinity of 1 over c e to the power ct, calculated at 0 and r. And when we finish this, we find that if c is a positive number, this limit is equal to infinity. If c is a negative number, then this is equal to minus 1 over c. One more example. The integral between 1 and infinity of 1 over t dt. This means the limit as r tends to infinity of the integral from 1 to r, 1 over t dt. That's the limit as r tends to infinity of the natural logarithm of t calculated at r and at 1. And that is equal to infinity. We're going to need the idea of piecewise continuous functions. Look at the function I've drawn at the top of this slide. This function has 4 pieces, but each of these 4 pieces is a continuous function. If we have a function which we can break apart into a finite number of pieces like this, and if each one of these pieces is continuous, then we say that the function is piecewise continuous. Let's be a little bit more precise. What we need is there to exist a finite partition. Let's say numbers t0, t1, t2, t3, etc., up to tn, where between each of these points we have a continuous function. I need f to be continuous on every subinterval from tj minus 1 to tj, and I need to have that all of the one-sided limits exist. At the left end and at the right end of each one of these pieces, the one-sided limit needs to be a finite number. Okay, now that we've revised these ideas, we're ready to start talking about the Laplace transform. Named after a Frenchman called Pierre-Simon Laplace. What is the Laplace transform? Well, what is derivative? What derivative does is it changes a function f into a new function, and the new function we call f prime. The Laplace transform is another way to change a function. The Laplace transform, which using a computer I'm going to write like this, changes some function, small f, into a new function. And the new function we're going to call capital F. For the new function, we're also going to change the independent variable. Instead of writing t, we're going to change this to s commonly. For the Laplace transform, we use a curly L. It's not an ordinary L, it's a curly L. If I was using a pen, I would write my curly L like this. You could do it like this, you can do it differently. Just make sure that your curly L doesn't look the same as your ordinary capital L. So make sure it's got some sort of curve to it, some sort of curl to it, so that it's a different symbol from your ordinary L. So let's do the definition of a Laplace transform. First of all, we need a nice function. Don't dwell too much on this. This is just me being careful. We need a function f which is piecewise continuous on each finite interval, and we need the function to not get too big too quickly. So that rule number 3 says it doesn't get too big too quickly. Don't worry about that. The key part of this definition for you is this formula. The Laplace transform of a function small f, which has domain interval between 0 and infinity, is a new function which is defined by this formula. It's the integral from 0 to infinity, e to the power minus st, f of t dt. This is a formula we're going to be using a lot over the next few slides. There's two ways that we're going to be writing the Laplace transform of small f. We can either use capital F, or we can write curly L of f. And I'm going to be using both types of notation interchangeably. Okay. One more thing to say before I move on. Capital F of s exists for small s greater than a, where a comes from rule number 3. Again, for this course, don't dwell too much on that. Just understand that sometimes capital F exists and sometimes capital F doesn't exist. Sometimes it's not defined. Okay, so this is the formula at the top we're going to be using. The Laplace transform of small f is the integral from 0 to infinity, e to the power minus st, small f of t dt. Over the next few slides, we're going to be using this formula. First, I want to do the Laplace transform of the easiest function that I can think of. Perhaps the easiest function that we could think of would be 0. What is the Laplace transform of 0? Well, it's just integral of 0, or 0. So perhaps I should have said the easiest function we can think of is 0, and the Laplace transform of 0 is 0. The Laplace transform of 1 next, the next easiest function that we can think of. Put the number 1, the function 1, into the formula at the top. We're doing the integral from 0 to infinity, e to the power minus st dt. And this is a type of integral that we've already done today. We did this on slide 2 or slide 3. Look back if you need to, or go through the calculation here. This is equal to 1 over s. And this is defined as long as s is strictly greater than 0. Let's do another function. What is the Laplace transform of the function e to the power 80? Let's calculate it. That's the integral from 0 to infinity, e to the power minus st, e to the power 80 dt. Finish the calculation. It's almost the same as the previous one. We get 1 over s minus a, and this is defined as long as s is greater than a. Now, note here that we started with a function e to the power 80, and the domain of the function we started with, the domain of our small f, was the interval between 0 and infinity. After we take the Laplace transform, we get a new function, the function 1 over s minus a, and this function has domain open interval between a and infinity. Next function. Here I have a piecewise defined function. This function is piecewise continuous. The function is equal to 1 if t is between 0 and 1. The function is equal to some number k if t is equal to 1. That number doesn't matter for us because we're going to be doing the integral. And the function is equal to 0 if t is greater than 1. What is the Laplace transform of this function? So we have the integral from 0 to infinity, e to the power minus st, f of t dt. When we do the integral, we don't care about the value of the function at 1. We can forget about that. We're only interested in the two pieces, between 0 and 1 and between 1 and infinity. Between 0 and 1, the function is equal to 1. So it's integral of e to the power minus st multiplied by 1. Between 1 and infinity, the function is equal to 0. So it's going to be plus the integral of 0, which is just 0. So really we're just doing the integral between 0 and 1, e to the power minus st dt. And when we finish this calculation, I'll leave this for you to check, we get the function 1 minus e to the power minus s divided by s. Next example. Find the Laplace transform of sine 80 for some constant a. So we're going to do the same thing. We have our formula at the top. We're going to be sticking in sine 80 into the integral. So I have capital G is the Laplace transform of small g. That's the integral from 0 to infinity, e to the power minus st sine 80 dt. And remember, anytime we do an integral between 0 and infinity, what we really mean is the limit as r tends to infinity of the integral between 0 and r. To calculate this integral, we're going to use integration by parts. Here, e minus st, which I've written in green, is going to be the u. And sine 80, which I've written in orange, is going to be the v prime. After we do integration by parts, we have uv first, so green function will stay the same, and then we're going to integrate the orange function. Integral of sine is minus cos, and then it's going to be minus the integral of u prime v. So we're going to differentiate the green function, and we're going to integrate the orange function. Here we are. Now, the first term, the limit as r tends to infinity of minus 1 over a e to the power minus st cos at calculated at 0 and r. What do we have? If we put 0 in, we get cos of 0. Cos of 0 is equal to 1. And e to the power 0 is also equal to 1. So if we're using 0, we're just going to be getting minus 1 over a, and then minus becomes plus. That's 1 over a. What do we do? What do we get if we use the r? We're going to get e to the power minus rt, e to the power minus a big number, which gets bigger and bigger. Take the limit of that, we get 0. So the first term is just going to be equal to 1 over a. And then the second term is just minus s over a, integral between 0 and infinity, e to the power minus st cos at dt. How can we calculate this integral? We can use integration by parts a second time. Again, we have the integral of a function multiplied by a function. So we use integration by parts again. This time, I'm not doing the details. I'm just asking you, please check that there's no mistakes here. Now, capital G we can write as 1 over a minus s squared over a squared, integral between 0 and infinity, e to the power minus st sine at dt. Why do we not get an extra term? Because sine of 0 is equal to 0. So there is no extra term. The first part of the integration by parts is just going to be 0. Again, we've got an integral of a function multiplied by a function, but this is the integral we started with. Actually, we've just got 1 over a minus s squared over a squared, capital G of s. We can just rearrange this equation to find a formula for capital G. Therefore, and again, I'm skipping the details, I'll leave this for you to check. The Laplace transform sine at, or capital G of s, is a divided by s squared plus a squared. Next, what is the Laplace transform of cos 80? It's almost the same thing, but instead of a on the top, we get s on the top. I'll leave this for you to prove. Do the same type of calculation that I did in the previous example. Do integration by parts 2 times, and then rearrange, and you will find that we get s divided by s squared plus a squared. Please do that. We could do the Laplace transform of sine 80, and this is almost the same as the Laplace transform of sine 80, but instead of s squared plus a squared on the bottom, we would get s squared minus a squared. Why? Because if we differentiate sine 2 times, we get sine, but if we differentiate sine 2 times, we get minus sine. That's why plus becomes minus. But other than that, the calculation would be the same. The Laplace transform of cos 80 is s over s squared minus a squared. And for these two formulae, I leave it for you to prove this. You should be able to use the integral definition to find these two formulae. The Laplace transform is linear. It's a linear operator. The Laplace transform of constant f1 plus constant f2 is equal to constant Laplace transform f1 plus constant Laplace transform f2. I leave this for you to prove. It just comes straight from the definition. It's because an integral is linear. So you can just write this down in just 2 or 3 lines, the proof. So, for example, if small h of t is 5e to the power minus 2t minus 3 sine 4t, what is the Laplace transform of this function? I want to find capital H of s, or using the other notation, I want to find curly L of small h of s. I want to find curly L, or the Laplace transform of 5e to the power minus 2t minus 3 sine 4t. And because the Laplace transform is a linear operator, we can split this up into 5 Laplace transform of e to the power minus 2t minus 3 Laplace transform of sine 4t. And these two we already know. We've done these already today. We can write down that the Laplace transform of e to the power minus 2t is 1 over s plus 2, and that the Laplace transform of sine 4t is 4 over s squared plus 16. So simplify and we get our answer. We also have an inverse Laplace transform, something goes backwards. And the way it's defined is if capital F is the Laplace transform of small f, then small f is the inverse Laplace transform of capital F. So, for example, the Laplace transform of 1 is equal to 1 over s. We've done that already. So that means that the inverse Laplace transform of 1 over s is equal to 1. The inverse Laplace transform is also a linear operator. Again, I'm going to leave this for you to prove. Let's move on to an example. Find the inverse Laplace transform of 10 over s squared minus 25. How can we do this? Well, we've seen something similar to this already. We know that the Laplace transform of sine at is equal to a over s squared minus a squared. So we're going to use this. We know that the number we want on the top should be the square root of the number on the bottom. If we have a squared on the bottom, we should have a on the top. And we don't quite have that. We have a 10 and we have a 25. So what we're going to do is we're going to divide by 2 so that we get 25 on the bottom and 5 on the top. And then that looks like the standard formula. It looks like a divided by s squared minus a squared. We know that the inverse Laplace transform of a over s squared minus a squared is sine at. So this must be 2 multiplied by sine 5t. Let's do another one. Find the inverse Laplace transform of 1 over s plus 1 over s minus 2. I'm going to use the fact that the inverse Laplace transform is linear to split this up into 2. The inverse Laplace transform of 1 over s. Look at the top, we know what that is. Plus the inverse Laplace transform of 1 over s minus 2. Again, look at the top, we know what that is. This is equal to 1 plus e to the power 2t. Time for another theorem. The Laplace transform of t to the power n, f of t, is equal to minus 1 to the power n multiplied by the nth derivative of capital F. And this is a theorem which I do want to prove. First, I'm going to do it in the case when n is equal to 1. So in the following, we're going to be proving the formula, but for n equal to 1. We're going to prove that the Laplace transform of t, f of t, is equal to minus 1 multiplied by the derivative of f with respect to s. So actually, I'm going to be starting with minus df ds, and I'm going to end up with the Laplace transform of t, f of t. Okay, so we want minus the derivative of capital F, but capital F is just integral from 0 to infinity, e to the power minus st, f of t dt. And let's just suppose that we're allowed to take the derivative inside the integral. Let's suppose we've dotted our I's and crossed our T's and we've checked all the rigorous proof, and we've seen we're allowed to do that for this type of function. Let's not worry too much about the details. That's the same as minus the integral from 0 to infinity, dds of e to the power minus st f of t dt. It's easy to differentiate an exponential function. Of course, the derivative of e to the power minus st is just minus t e to the power minus st. There's two minus signs here. They're going to cancel out. And I'm going to move the t next to the f of t. Think of the t f of t now as one function. But then that is just the Laplace transform of t f of t. So that proves that the formula is true for n equal to 1. If we use this formula 2 times, we could also prove that the formula is true for n equal to 2. And then if that's true, we can use the formula again. It must be true for n equal to 3, for n equal to 4, or for any n. I'm going to skip the details here. Okay, so now we have this formula. We can use it to calculate the Laplace transform of t squared cosh 2t. Let me remind you that the Laplace transform of cosh at is s over s squared minus a squared. And we've just created the formula. Where are we? Here we are. We've just found the formula that we want to use. Which is that the Laplace transform of t to the power n f of t is minus 1 to the power n, nth derivative of capital F. And that's similar to what we have. We have the Laplace transform of t squared multiplied by a function. So using the formula, that must be the same as minus 1 squared multiplied by the second derivative of the Laplace transform of cosh 2t. In other words, the second derivative of s over s squared minus 2 squared. And I'm not going to do the details here. I'll leave this for you to check. It's just using the quotient rule for derivatives 2 times. You can check that there's no mistakes here. We can also use this formula to calculate the Laplace transform of t to the power n. We're going to think of t to the power n as t to the power n multiplied by 1. And then we're going to be using the formula at the top. That must be the same as minus 1 to the power n multiplied by the nth derivative of the Laplace transform of 1. You will recall that the Laplace transform of 1 is 1 over s. So we're going to be doing n derivatives of 1 over s. And the nth derivative of 1 over s is minus 1 to the power n factorial over s to the power n plus 1. Check it. The minus 1's cancel out, and we just end up with n factorial over s to the power n plus 1. Okay, now it's time to go through some of the, just to recap and look at the standard elementary Laplace transforms of the basic functions and the standard theorems. In the exam, you'll be given something like this, although perhaps not with every line. What have we done already today? Laplace transform of 1, we've done that. Laplace transform of e to the power at, we've done that. Laplace transform of t to the power n, we've just done that. Sine, cos, sine, and cosh, we've talked about these already. I've shown you the proof for sine 80, and the other 3 I'm leaving for you to do. Let's scroll down a little bit. E to the power 80 sine bt and e to the power 80 cos bt. We didn't do these yet. We'll look at these later today or next lesson. T to the power n, e to the power at. You've seen enough to be able to do this. You've seen how we calculate the Laplace transform of t to the power n multiplied by a function. So you could do this now. The next 3 we'll talk about next lesson or the lesson after that. Ignore those for the time being. We're not ready for those yet. Scroll down a little bit more. And what else do we have? Again, f of ct we'll look at later. Integral from 0 to t, f of t minus tau, g tau, d tau. That's a convolution integral. We'll look at that in 2 or 3 weeks' time. And the final one we have done. The final one we've just done. The Laplace transform of t to the power n f of t. I've just proved, at least in the case n equal to 1, I've proved that this is minus 1 to the power n, nth derivative of capital F. Let's do another example. Find the inverse Laplace transform of capital F is equal to the natural logarithm of 1 plus 1 over s squared. I want to use the same formula again. I want to use the Laplace transform of t to the power f of t is minus 1 to the power n dnf ds squared. But I'm going to use it for in the case when n is equal to 1. Why? Because ln of 1 plus 1 over s squared, nothing like that appears on the table of elementary Laplace transforms. But when we differentiate ln, we get 1 over something. And 1 over something will appear, or something like it appears on the table of elementary Laplace transforms. So we're going to be differentiating capital F, and then and first multiplying it by minus 1, and then we're going to find the inverse Laplace transform of it. We're going to find that t multiplied by the answer that we want to find small f of t, is minus the inverse Laplace transform of df ds. That's our strategy. Okay, so we're starting with capital F is the natural logarithm of 1 plus 1 over s squared. The first thing I want to do is I want to differentiate this. We differentiate it, we get minus 2 over s cubed, all divided by 1 over 1 over s squared. Let's multiply by s cubed to simplify this a little bit. That's the same as minus 2 over s squared plus 1. So t multiplied by f of t, that's t multiplied by the answer that we want, is going to be the inverse Laplace transform of 2 over s squared plus 1. To proceed, we need to use partial fractions. We need to write the function 2 divided by s squared plus 1 in partial fractions. I'm going to revise partial fractions very quickly here. This should be revision for you from Mathematics 2. You should know everything I'm doing here, so I can go through quite quickly. Using partial fractions, it's going to be something over s plus something over s squared plus 1. And what is the something? Well, something is always going to be a polynomial of degree 1 less than the denominator. Because s is a first degree polynomial, on the top I'm just going to have a number. Because s squared plus 1 is a second degree polynomial, the rule is that on top I need to have a first degree polynomial. So this is going to be some number a over s plus some number bs plus some number c divided by s squared plus 1. Let's find a, b, and c. Put everything over the same denominator. Gather the terms together. I get a plus bs squared plus cs plus a. And that needs to be the same as 2. So a plus b must be 0, c must be 0, and a must be 2. So in partial fractions, our function is the same as 2 over s minus 2s over s squared plus 1. This is the function that we want to find the inverse Laplace transform of. So how can we find the inverse Laplace transform of 2 over s minus 2s over s squared plus 1? Let's bring up our table of elementary Laplace transforms. If you received my email, you may have this printed out in front of you or open another tab on another screen. On this table, I'm looking for something that looks like 2 over s, and I'm looking for something that looks like 2s over s squared plus 1. So have a quick look. Do you see anything that looks like these? For the first term, I have a 1 over s in the table. Don't worry about the constant 2. We'll deal with that later. It's the same type of function as this. What about the 2s over s squared plus 1? And we're not too worried about the number 2. That looks like this. That looks like the Laplace transform of cos at. So let's remove our table of elementary Laplace transforms and let's just write what we have. I've written at the bottom, we're going to be using the Laplace transform of 1 is equal to 1 over s, and the Laplace transform of cos at is equal to s over s squared plus a squared. Now that I know which of the standard elementary Laplace transforms I'm going to use, I know how to break up my function. I'm going to break my function up into 2 multiplied by the inverse Laplace transform of 1 over s minus 2 multiplied by the inverse Laplace transform of s over s squared plus 1. Because that's just 2 minus 2 cos t. And then we're almost finished. We want to find small f of t, so all we need to do is divide both sides by t. The answer to this question is 2 multiplied by 1 minus cos t, all divided by t. Great, but why are we studying the Laplace transform in a course about differential equations? Because it's a useful technique which we can use to solve some initial value problems. Why? It all comes down to this important formula just here. The Laplace transform of f prime is the same as s multiplied by the Laplace transform of f minus f of 0. This whole chapter, this whole idea of using the Laplace transform to solve differential equations, to solve initial value problems, comes from this very important formula. We have a similar formula for the second derivative. The Laplace transform of f double prime is s squared multiplied by the Laplace transform of f minus s of f0 minus f prime of 0. We have one for the Laplace transform of f triple prime. And the pattern is the same, look. 3 derivatives means we start with s cubed. Second term is s squared, third term is s, and then the fourth one is s to the power 0 or 1. And then the pattern is f at 0, f prime at 0, f double prime at 0, and so on. We could do the Laplace transform of 4 derivatives of f, or 5 derivatives of f, or n derivatives of f. The pattern is we start with Sn, and then we go down to Sn minus 1, Sn minus 2, and so on. Always start with s to the power same number as the derivatives of f, and then decrease each term. From the second term onwards, we do f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and so on. Because these are so important, let's prove these. I'm going to prove 1 and 2. I'm going to leave 3 and 4 for you to prove. How can we prove formula number 1? We can prove it using integration by parts. Starting with the Laplace transform of f prime, that's integral from 0 to infinity, e to the power minus st f prime of t dt. Using integration by parts, for the first term, green function stays the same. For the orange function, we integrate it. So e to the power minus st f of t, calculated at 0 and infinity. And I've been a little bit lazy here. When I do an integral from 0 to infinity, really I mean the limit as r tends to infinity of the integral from 0 to r. I'm just being a little bit lazy. I assume you know what I mean here. Minus the integral from 0 to infinity. We differentiate the green function and we integrate the orange function. It's easy to differentiate an exponential function. So what do we have? If we put infinity in, we get e to the power minus infinity, and that's just 0. So just 0. If I put 0 in, I'm going to get e to the power 0, which is 1, multiplied by f of 0. In other words, I'm just going to get f of 0. Minus the integral from 0 to infinity, minus s e to the power minus st f of t dt. Right, so that's just minus f of 0 plus s multiplied by the integral from 0 to infinity e to the power minus st f of t dt. But what is this written in red? This should look familiar to you by now. What is this red thing? This red thing is just the Laplace transform of small f. And that's it. That's the formula that we wanted to prove. It's just an integration by parts. Now that we have this formula, now that we have the formula we've just proved, we can use this to prove number 2. Take this formula and everywhere you see an f, replace it by f prime. So instead of f just here, we write f prime. Instead of f just here, we write f prime. And instead of f prime, we write f double prime. All I've done here is I've taken the formula at the top and I've replaced every f by f prime. But we know that the Laplace transform of f prime is just s Laplace transform of f minus f of 0. So this is just s squared Laplace transform of f minus s f of 0 minus f prime of 0, which is the formula in part 2. All I've done is I've used the formula in part 1 2 times to prove the formula in part 2. Parts 3 and 4 I'll leave for you to prove. Just keep using the formula again and again and again, and you can prove that they are true. Great. So now let's look at an initial value problem. Solve y double prime minus y prime minus 2y is equal to 0 with the initial conditions y of 0 is 1, y prime of 0 is equal to 0. And I'm going to solve this problem 2 times. First, I'm going to use the method from chapter 3. In chapter 3, how do we solve it? First, we did the characteristic equation to find the roots of the characteristic equation. As soon as we know the roots, we know the general solution to the differential equation. And then to finish the problem, we just need to find the constants C1 and C2. And in this case, the constants are 2 over 3 and 1 over 3. So the solution to this problem is 2/3 e to the power minus t plus 1/3 e to the power 2t. Just remember this. We're going to solve the problem another way now, and you'll see that we get the same answer. How can we use the Laplace transform to solve an initial value problem? Typically, we're going to be using the Laplace transform to solve a difficult differential equation. For this first example, we don't have a difficult differential equation. We have a very easy one, but later on, we're going to be using it for more difficult differential equations. And let's suppose that instead of solving this directly, and then maybe it's too difficult for us to solve it directly, what we're going to do is we're going to use the Laplace transform to change our difficult differential equation for small y into an easy equation for capital Y. An easy equation we can solve to find capital Y. If we know capital Y, perhaps we can then use the inverse Laplace transform to find small y. So let's use this technique to solve our first example, our differential equation, which is actually easier, we already know the answer to. So first, we're going to take the differential equation and we're going to take the Laplace transform of both sides. The differential equation is that y double prime minus y prime minus 2y is equal to 0. So that means that the Laplace transform of y double prime minus y prime minus 2y must be the same as the Laplace transform of 0. And remember that the Laplace transform of 0 is equal to 0. I'm going to write the left-hand side as the Laplace transform of y double prime minus Laplace transform of y prime minus 2 times the Laplace transform of y, because the Laplace transform is a linear operator. There's two formulae at the top that we're going to be using. These are the ones from the theorem. The Laplace transform of y prime is s capital Y minus y0, and the Laplace transform of y double prime is s squared capital Y minus sy of 0 minus y prime of 0. So our equation becomes s squared capital Y minus sy0 minus y prime of 0 minus s capital Y minus y of 0 minus 2 times capital Y is equal to 0. At this point, we put the initial conditions in. Y of 0 was 1 and y prime of 0 was 0. So this just simplifies to s squared capital Y minus s minus 0 minus s capital Y minus 1 minus 2y is 0. Or rearranging this to put all of the y terms together, this is the same as s squared minus s minus 2 capital Y plus 1 minus s is equal to 0. Rearrange this a little bit further. That's the same as capital Y is s minus 1 over s squared minus s minus 2, or s minus 1 over s minus 2 multiplied by s plus 1. We need to find the inverse Laplace transform of this function, and then we will have our solution to the initial value problem. How do we find the inverse Laplace transform of something like this? We need to use partial fractions. Let me show you the whole calculation. You can check this when you re-watch the lesson or read the lecture notes. You can check that this is the same as 1/3, 1 over s minus 2, plus 2/3, 1 over s plus 1. And these should look familiar to you. 1 over s minus 2 and 1 over s plus 1. Recall that the Laplace transform of e to the power 2t is 1 over s minus 2, and the Laplace transform of e to the power minus t is 1 over s plus 1. So, small y, that's the inverse Laplace transform of capital Y, must be 1/3 inverse Laplace transform of 1 over s minus 2 plus 2/3 inverse Laplace transform of 1 over s plus 1, or 1/3 e to the power 2t plus 2/3 e to the power minus t. And of course, that's exactly the same answer that we got using the method from chapter 3. For an easy equation like this, of course, it's easier to use the method from chapter 3, but we're not going to be using the Laplace transform for easy equations. We're going to be using the Laplace transform for more difficult equations. For more difficult equations, this is going to be the only method that we can use. Let's do another example. Solve y double prime plus y is equal to sine 2t with the initial conditions y of 0 is 2, y prime of 0 is equal to 1. So let's go through the method very quickly. We start with the differential equation and we take the Laplace transform of everything. The Laplace transform of y double prime plus the Laplace transform of y is equal to the Laplace transform of sine 2t. We use the formulae for the Laplace transform of sine 2t and for the Laplace transform of y double prime. That's the same as s squared capital Y minus sy of 0 minus y prime of 0 plus capital Y is equal to 2 over s squared plus 4. And at this point, it's time to use the initial conditions. Instead of y of 0, we have a 2. Instead of y prime of 0, we have a 1. So that's just s squared capital Y minus 2s minus 1 plus capital Y is equal to 2 over s squared plus 4. We need to rearrange this so that we get capital Y is equal to something. What I'm going to do is I'm going to take the minus 2s minus 1 over to the right side of the equal sign. We will get s squared plus 1 left, and then I'll divide both sides by s squared plus 1. Divide both sides by s squared plus 1. Here we go. Capital Y is 2s plus 1 over s squared plus 1 plus 2 over s squared plus 1, s squared plus 4. We need to find the inverse Laplace transform of this function, so we need to write this in terms of partial fractions. This should be revision for you. I want to write this as 2s plus 1 over s squared plus 1 plus as plus b over s squared plus 1 plus cs plus d over s squared plus 4. And I'm going to skip the details here. I'll leave this for you to check. After we've calculated a, b, c, and d, we can find that this is the same as s squared plus 1 over s, as 2s plus 1 over s squared plus 1 plus 2/3 over s squared plus 1 minus 2/3 over s squared plus 4. The first two terms are both over s squared plus 1. I have the number 1 and the number 2 over 3. I want to combine these together. 1 plus 2 over 3 is equal to 5 over 3. I need to find the inverse Laplace transform of this function. So what I do is I pull out my table of elementary Laplace transforms. You might have this in front of you now, and I'm looking on the table of elementary transforms for things which look like these functions. So I know how to break it up, how to take the constants out. And after I've done that, I know to take the number 2 out of the first one, to take the number 5 over 3 out of the second one, and to take the number 1/3 out of the third one. Why is it 1/3 here? Why is this not 2/3? The answer is, on my table of elementary Laplace transforms, I cannot find 1 divided by s squared plus 4, but I can find 2 divided by s squared plus 4. And then after I know that I need to keep 2 inside the bracket, I only have 1/3 to take out of the bracket. So what do we have? We have 2 multiplied by the Laplace transform of cos t plus 5/3 multiplied by the Laplace transform of sine t minus 1/3 multiplied by the Laplace transform of sine 2t. And as soon as we know that, we know the answer to this problem must be small y is 2 cos t plus 5/3 sine t minus 1/3 sine 2t. I have one more example for today's lesson. This time we have a 4th order linear differential equation. 4 derivatives of y minus y is equal to 0 with the initial conditions y of 0 is 0, y prime of 0 is 1, y double prime of 0 is 0, y triple prime of 0 is equal to 0. So what do? We start with the differential equation and we take the Laplace transform of both sides. 0 is equal to the Laplace transform of 4 derivatives of y minus the Laplace transform of y. It's 4, so we start with s to the power 4, capital Y, and then it goes s cubed, s squared, s, and then just 1. And the initial conditions increase. Y of 0, y prime of 0, y double prime of 0, y triple prime of 0. That's the pattern. We can put the numbers in because y prime of 0 is equal to 1, but the other 3 are equal to 0. That's 0, 0, 0, and we're going to get a 1 just here. So it's just s to the power 4 capital Y minus s squared minus capital Y, or s to the power 4 minus 1 capital Y minus s squared. And that rearranges to s squared over s to the power 4 minus 1. We need to find the inverse Laplace transform of this function. So we need to use partial fractions. We can factorize the bottom as s squared minus 1, s squared plus 1, and then using partial fractions, I'm giving no details here, I'll leave this for you to check. That's the same as a half over s squared minus 1 plus a half over s squared plus 1. And then we can write down the solution. Small y, that's the answer to the initial variable problem, must be a half multiplied by the inverse Laplace transform of 1 over s squared minus 1, plus a half multiplied by the inverse Laplace transform of 1 over s squared plus 1. That's just a half sine t plus a half sine t. And for the final slide of this week's lesson, I have a graph of this function. This is the solution to this initial value problem. Next week, there's no lesson for this course. I wish you good luck for your exams for other courses. In 2 weeks' time, we will continue using the Laplace transform. Chapter or section 4.3 will be revision, really. It will carry on the same ideas from today's lesson. And then the meat of the next lesson will be section 4.4, when we will start talking about step functions. Are there any questions?